Remember, chemists like to predict things. We like to predict if a particular reaction will proceed forward or if it's not going to go forward. If it doesn't go forward, we want to be able to manipulate things. We want to be able to take that process and make it go forward, and become more effective and getting a better yield. So the question is, how can we predict these things? Enthalpy, or delta H, is one key component to this. And basically, what we say back in chapter 5 of the textbook is, well, enthalpy is kind of a good way to predict this, but doesn't happen in every case. And later in this chapter, we're going to go over some examples of how just using enthalpy doesn't do as much in terms of predicting if a reaction is spontaneous. So what we have to do is we have to introduce a new term considering the thermodynamics, and that term is called entropy. And what entropy is going to be able to do is it's going to be able to allow us to predict if a particular reaction is what we call spontaneous. So the next topic we're going to look at is entropy and spontaneous process. So let's define what the term spontaneous process is. A process is spontaneous if it occurs without outside intervention. A spontaneous process may be fast or slow. So do not confuse spontaneous process and any of these thermodynamic quantities with kinetics. They're completely different sub-areas of chemistry. So thermodynamics can only tell the direction in which a process will occur, but nothing about the speed. So the question is, what type of information can we get from thermodynamics, and what type of information can we get from kinetics? You've heard the slogan from all these jewelry manufacturers that a diamond is forever, right? Well, chemists are like, that's not true. That's not thermodynamically possible, right? Because it's a spontaneous process for a diamond to be converted over to graphite. Okay, that's the process that's spontaneous. Okay, but if you have a piece of jewelry today and you look at that diamond, it's not converting in real time, looking down at your finger on your ring. That process could take millions of years. None of us is going to live that long, so we really don't notice any type of conversion here. So thank goodness for kinetics, which tells us that this reaction is not going to happen at any appreciable speed. So what we can look at with thermodynamics is, does a reaction go forward, yes or no? It tells us little to no information about the speed of that particular reaction. So if we look at these reaction energy diagrams that we've drawn in previous chapters of the book, where we have energy on the y-axis and the reaction progress on the x-axis, we can typically say, hey, we have a reactant up here, and then we have products down here. When we draw this energy diagram, there's typically an activation energy barrier to go from reactant to product. What thermodynamics tells us is the relative energy of the reactant and the energy of the products. So this area of each of these diagrams is what thermodynamics will tell us about a particular reaction mechanism. All of this stuff here in the center, this is kinetics. These are two completely different fields telling us two completely different bits of information. So we have thermodynamics to care about, and we have kinetics to think about. The kinetics, what that wants to tell us is, how fast can I get from here over to here? When we talk about kinetics, we really don't talk about much in terms of energy. Okay, there's activation energy, but that's about it. And we want to know how we can lower that activation energy. When we talk about thermodynamics, there's a change in energy between the reactants and the products. And all thermodynamics cares about is, where do I start and where do I finish? You'll hear this term called state function. And state function is tied to a lot of our thermodynamic quantities, because a state function is what we call independent of path. So it doesn't matter if we have a small activation energy, a large activation energy, or an activation energy somehow in between. All we're predicting with thermodynamics is this energy difference right here. We don't care how you got there or what you did. We just want to know what is the energy difference between the reactant and the product. So that's what we're going to talk about and what we're going to start analyzing in this particular chapter. Is what is the energy difference between the reactants and products? How can I make a reaction favorable? How can I make it more favorable, more cost efficient? And if something doesn't want to happen, can I influence it and make it happen? So here's a process that we look at. The question is that process spontaneous or is it not spontaneous? And the driving force for a spontaneous process is an increase in entropy. So we need to define this term entropy. Entropy is a measure of randomness or disorder. And what we can say about entropy is, in order to have a small entropy, we need to have a highly ordered system. If we have a large entropy, we have a highly disordered system. And we're going to be talking about, when we talk about these thermodynamic quantities, we will talk about changes in entropy. So how is entropy changing from state 1 to state 2? How does the entropy of water in the solid state when it's an ice cube compare to when water is steam? How ordered are they? if I have a highly ordered structure, that's like a solid, right? It's going to have a small entropy because I'm packing everything together in a closed, packed environment. When I have a gas, it's highly disordered. So all of its particles are moving in constant motion. They're rotating around. They're tumbling. They're knocking into each other. Whereas in a solid, the energy is restricted and there's some vibrations, but they're not moving much. So these are some comparison about entropy, and when we go from a solid to a gas, we can analyze those entropy changes. So we can also say a couple more things about this entropy.